So we've got this flow chart of reactions. I'm not sure why I haven't shared my screen yet. And at the end of last week, I kind of bailed last minute. We were about to write down the names for all of these reactions. What I want to do this time instead is start to get into them a little bit at a time, and like one at a time, and then we'll name them as we get into them. If it's useful for you, on this sheet, I've numbered the reactions 1 through 8. I guess I didn't number the other 9, 10, and 11. I don't know why. And I originally did that because I was going to have another line on here where you could just write down all their names, and then I decided not to go for it because it wasn't formatting well, and I didn't know that it would fit well. So that is just kind of for you to keep track of them. Those numbers are irrelevant. Those numbers are insignificant. If it helps you, you can organize those 8 and kind of write their names somewhere else so that you can keep track of them. For now, let's dive into the first reaction going straight up, and this was HX addition. Although we can also refer to this as halo. Nope. We can also refer to this as hydrohalogenation. Does that seem like a fair name, hydrohalogenation? Good. We're adding a hydrogen, we're adding a halogen, HX addition. The reagents for this, what we'll write over the reaction arrow is simply HX. I'm going to clarify the nature of HX. The 3 most common ones that you'll see are HCl, HBr, and HI. And to be fair, I don't put HI very often. In our class, we're going to see HCl and HBr a lot. Those are very common acids to work with. In some places, you'll see this run with a solvent. Sometimes they'll put THF, sometimes they'll put something else. These reactions for this common starting material will give us this product. Now, if you have multiple colors and you want to highlight something, we can highlight the X and the H that have added in a different color. So the X should be very obvious. But where is that hydrogen that added across the alkene during this reaction? Is it on the secondary carbon or the primary carbon? Secondary? Secondary? If the hydrogen from this reaction, HX, added to the secondary position, then there would be a vacancy at the primary position. That would result in a primary carbocation. But those are not very stable. So it's much more likely that the alkene accepted the hydrogen at the primary carbon and left a vacancy at the secondary carbon, a secondary carbocation. But a secondary carbocation can and will rearrange if an adjacent carbon is more stable than it, which means this hydrogen migrated to the secondary position and left in its wake a new carbocation where the halogen was able to add. So what I want you to recognize in this reaction, you know what, I'm gonna change route a little bit, because if I put all those names in there, it's gonna get so messy. Some of the notes that I want you to have on this reaction, most importantly, it has a carbocation intermediate. Why is that important? If a reaction does not have a carbocation intermediate, then the reaction cannot rearrange. Carbocation rearrangements only occur if there's a carbocation. If there is a carbocation intermediate, I need to be mindful of the possibility that the structure may rearrange during the reaction. So this is an important note to have. The other note about this, and there's a few ways that we can try to illustrate this in an example reaction like this. The stereochemistry that the hydrogen takes on. Recognize that this alkene carbon is not chiral. It can never be chiral. And this primary carbon specifically, oh, I'm sorry, that looks really confusing, doesn't it? Is anybody going to tell me? I put an X where I meant to put an H. Sorry. Just got mixed up. This primary carbon is not chiral. But if it was chiral, one question we should ask is, what chirality does it take? Does it take an S configuration or does it take an R configuration? The fact of the matter is the alkene is flat, which means that it can add the hydrogen from either side, which means you can have either configuration, R or S. And how do we represent either? We can show that as a squiggly line. All right, I'm going to backtrack, because if you are someone that likes to show your dashes as squiggles, now is the time to stop, because a squiggle, although it doesn't usually get wider, it usually just stays like a normal line. A squiggle indicates not R, not S, not short. The squiggle means it could be either one without any clarity. And now the same thing happens here to the halogen. This also adds with that squiggle. Not R, not S, could be either. Although, let's be clear again, in our example, this is also not a chiral carbon, but I'm trying to give you a generic overview of what this reaction can produce on a specific example with information that you can kind of extrapolate to other examples. So, some more notes about this. Yes, it has a carbocation intermediate. Also, it adds the two groups randomly. So we can call this random addition. Do you remember what the alternatives are for stereo addition, stereo-specific reactions? The two groups can be random, or they can be locked relative to each other. When they both add to the same face, we call it blank addition, syn addition. And when the two groups add to opposite faces, we call it trans is a good guess. Anti addition. This reaction is not syn, it's not trans. Sorry, it's not syn, it's not anti. You got me. This reaction is random. When chiral centers are produced, they're produced randomly. They have no relationship to each other. That's to say, if one chiral center is formed, you will have both configurations. If two chiral centers are formed, you will have 4 different combinations. One where they're both R, one where they're both S, and one where every other one is R or S.
So wait, so everywhere there's a chiral, it randomly is R or S, is that what you're saying?
Correct.
Okay.
For random addition, every chiral center is randomly all combinations. So to be clear, this is information about the regiochemistry. No, I'm sorry. Can we start today over? Here we're describing the stereochemistry. And we also want to describe the regiochemistry. Carbocation formation is a little bit of an indicator about regiochemistry because it tells you the carbocation will form on the most substituted carbon. But a dead guy once said, when hydrogen adds to the carbon with more hydrogen, name it after me. Okay, so here is the rule. Markovnikov addition explicitly says H adds to the carbon with more H. Which of these two carbons has more H? The one on top, the less substituted hydrogen, the less substituted carbon. Here's 1H, here's 2H. Just the carbons of the alkene. And where did hydrogen add? It added to the less substituted carbon. Why did the hydrogen add to the carbon with more hydrogen? Stability of what? The hydrogen? Not the stability of the halogen inherently, no. There is a partial negative on this side of the alkene. That's the stereo-specific reactivity. We say that the less substituted is more negative, the more substituted is more positive. So if we're talking about stability, it's stability of the carbocation intermediate. If hydrogen had added to the carbon with more hydrogen, I would have formed a primary carbocation. You guys remember we had this example of a mechanism and it had two possible carbocations that could form? Well, here's an example there. These are my two possible carbocations. Which one will form? The more stable. Which one is more stable? The one that experiences the most hyperconjugation or resonance. And which one has the most hyperconjugation, that moral support? The more substituted carbocation. So hydrogen adds to the carbon with more hydrogen as a result of the most stable carbocation intermediate forming. It has nothing to do with hydrogen, and it has everything to do with stabilizing the positive charge. So Markovnikov's rule is all about hydrogen, which sucks. But what can you do? All right, so throughout our reactions, I'm going to give similar notes to this. I'm going to give a note whether it has a carbocation intermediate or some other type of intermediate. And I'm going to give notes on its regiochemistry and its stereochemistry. So it might be good to have a separate sheet that you can compare this to. I want to say, in the past, I've never taught it quite like this, but instead I would have had this reaction with our reagents, with our product, kind of right in here, right before the notes. And then I would have just listed out every single one of them. In fact, you can go back to my YouTube playlist from my summer Alkene lecture, and that's exactly how I run through all the reactions. Maybe this diagram doesn't help you remember it. Maybe it does. Maybe you want to take the effort in class to rewrite what I put in this diagram as a simple list of reactions. It's totally up to you. Our second reaction we'll consider is the X2 addition, also called, who remembers this one? Halogenation. The reagents over the reaction arrow for halogenation are simply X2. I'm going to put this next part in parentheses because it's not something that I will show you often, and it's not something that I'll require from you. but there are places you'll see that list THF as a solvent. Does anybody remember which category of solvents THF fell under? As a reminder, we had nonpolar, polar aprotic, polar protic, and that polar protic also included water, aqueous solvent. Polar aprotic. It's a good guess. And here's the structure, because THF is a little bit meaningless if you don't know its structure. And does this verify that THF is polar aprotic? There's no acidic proton, but there is a dipole moment. All right, that's important because the reaction after this changes to a polar protic solvent. But as long as you see X2 and nothing else, you should assume that it's in a polar aprotic solvent, because the polar aprotic solvent has no reactivity in this reaction. So it's okay to ignore. Once again, the versions of X2 that you'll see are Cl2, Br2, and I2, with an emphasis on Br2 and Cl2. Those are the most common ones that we will use this semester. Does this reaction have a carbocation intermediate? Debate. What do you think? Why? I mean, two things added here as well. So how can we phrase this? The fact that something didn't move to the other side tells us there's no carbocation intermediate. How can we phrase that? If there was a carbocation intermediate, we would have seen a rearrangement. We know that because we already saw a reaction with a carbocation intermediate and it rearranged. No rearrangement, no carbocation intermediate. No carbocation. Instead, this has a halonium intermediate. And halo is there just as an indicator of halogen, so that's chloronium, bromonium, iodonium intermediate. And the halonium intermediate looks like this. It's a three-membered ring with a positive charge on the halogen. How many bonds do halogens typically make? One. So when a halogen has more than one bond, it's sharing more often than it wants to. It takes on a positive charge. This is our halonium intermediate. The positive charge is not on a carbon. We're going to look more at this intermediate when we get into the mechanisms later. Can you give me some stereochemistry about this reaction? Is it random? Is it syn? Is it anti? Anti-addition. Because instead of squiggly lines, I've given you one wedged, one dashed halogen. How many chiral centers formed in this product that I've given? No. 1. Primary carbon is not a chiral center. It has 2 hydrogens. And this tertiary carbon is not a chiral center. It has 2 methyl groups. So really, this is the only chiral center. So why then did I show this as a wedge? This is not the lowest energy state. This has a different conformer where it rotates the largest group, the halogen, to be in a zigzag formation. This is not the lowest energy. So why do I show it as that then? To indicate to you that it's anti-addition. You don't always see anti-addition because you don't always create 2 chiral centers. So it would have been just as legal to draw this with a single line and only indicate the dash or the wedge that appears at the other position, but then you don't see what the anti-addition looks like. All right, one more question about this, which is that the only stereoisomer that can form? Who's missing one of these? Oh, yeah, got one more for you. Any other stereoisomers formed in this? You're missing one too? Okay. Hang on. I've only got one left. Okay. You sure? Oh, great. All right, ask yourself this question. Why did I draw the stereoisomer that I did? Why did I draw this halogen wedged and this halogen dashed? Is there not an equally anti-addition product? That looks like this? That seems feasible, does it not? So how can we represent that in a little bit of a shorter way? Rather than drawing both anti-addition structures, I could just draw one and then say racemic. Who can define racemic? Specifically, 2 enantiomers. Good. Racemic is that 50-50, exactly 50-50 mixture of 2 enantiomers. All right, now in this case, it is true that I did show 2 enantiomers, but not every halogenation reaction forms enantiomers. Sometimes there's another chiral center somewhere in the molecule that doesn't change. That gives you diastereomers. But the situation holds that when you have an anti-addition product, you can form it anti-addition one way, anti-addition the other way. So the other way that you could write this is plus stereoisomer, or plus other anti. All right, I'm trying to give you guys some baseline in these first couple of reactions because the rest of them are going to go a little bit more quickly. We're going to go through them a little bit more quickly. The last thing to talk about here is the regiochemistry. Would this reaction qualify as being Markovnikov or anti-Markovnikov? No hydrogen involved, so we really don't have anything to say here. Reaction number 3 is our haloether halohydrin addition. What we're saying in there is I'll add an X group to one carbon, I'll add an OR group to one carbon. haloether. Or I add an X group and an alcohol, halohydrin. Haloether, halohydrin. The reason that these are written together is because their reagents are very similar. If I have X2 in alcohol, the alcohol is a precursor to the ether. If I have X2 in water, water is a precursor to alcohol. What change did both the water and the alcohol go through in these reactions? I think you're getting at something, but there was not a loss of two equivalents of H2, of like H2. Instead of naming it, you want to just address what you're seeing?
Taking hydrogen.
Both the water solvent and the alcohol solvent lost a hydrogen. ROH bonded to another carbon and lost H. HOH bonded to a carbon and lost H. So there's a byproduct in these reactions. There's an equivalence of X that is gone, and there's an equivalence of H that is gone. And so both of these have a byproduct of HX. How acidic is HX in general? Very acidic. Which means that if HX is forming in the presence of an alcohol, you don't actually have HX, because HX will protonate the alcohol. This typically looks like ROH2 plus balanced by X minus, or H3O plus and X minus. That's the realistic byproduct. If HX forms in a solution, no, it didn't. It deprotonates, it readily dissociates. It's such a strong acid that it will protonate your solvent. That's one way to look at it. One small change. Typically, these are written with commas. X2, comma, ROH, X2, comma, H2O. And just to be clear, this halogenation reaction was in an inert solvent. The solvent does not react. Haloether, halohydrin is when the solvent does react. This is when the solvent takes a role in the reaction. This reaction also has a halonium intermediate. Great. In terms of predicting a mechanism, halogenation and haloether halohydrin addition, they start the same. They form the same intermediate. It's this intermediate that the polar protic solvent can actually react with. The polar aprotic solvent doesn't. Stereochemistry is anti-addition. But the regiochemistry, is it Markovnikov or anti-Markovnikov? There's no hydrogen, so you can't describe it by Markovnikov's rule. And this is why I don't like Markov-McDonald. But is it regio-specific? Yeah, I demonstrated that the halogen always adds to the less substituted carbon, and whatever the solvent was, that oxygen attaches to the more substituted position. So there is regiochemistry. Solvent attacks at more substituted position. Questions so far? Natalie first.
So this one is into carbon cation, right? So that's why it attacks at the secondary carbon versus the tertiary.
Correct. This one has a halonium intermediate,
So that's instead of the carbon.
and that halonium intermediate spans the two carbons of the alkene and the halogen itself. So on that halonium intermediate, the solvent will be a nucleophile to the more substituted of the two carbons. And we can actually, we had that partial negative, partial positive before. That doesn't go away in the halonium intermediate. There's still a more stable positive charge on the more substituted carbon, and still a more stable negative charge on the less substituted, even though it has a halonium sitting on top of it. And so where is the solvent's partial negative most attracted? To the partial positive carbon, to the carbon that is losing its electrons more substituted. Good.
Thank you.
One follow-up to that, which is about the name halonium. Do you guys know what else ends with -ium? Calcium. Helium. That's an outlier. Plutonium, sodium, potassium, lithium, beryllium, magnesium. A lot of cation forming species end with -ium. -ium is a suffix that indicates cation nature. Halonium has a positive charge, just like sodium, potassium, calcium, magnesium. Not helium. Helium does end with -ium, and I don't know how it got that name. Aiden, you had a question.
I had the same one as Natalie, actually. So.
Great questions. All right. Maisie.
Is the H2O the solvent? I'm just confused with the colors.
It depends. Alcohol can be the solvent. Water can be the solvent.
So why is the alcohol orange? Oh, okay. My brain's not.
It's okay. Thank you for addressing this. This is a very common issue. Most students will suspect that the alcohol will break its carbon-oxygen bond and attach to the alkene as OH. But it doesn't. The carbon-oxygen bond is actually fairly strong. The carbon-oxygen bond is challenging to break. Instead, the OH bond is very easy to break. So oxygen in the alcohol bonds to the carbon in the alkene, actually the carbon of the halonium ring. And then it tries to lose a bond. What's the easiest bond to break? OH. So it kicks off the H and it leaves us with OR and ether. So I want to say this one more time so that we catch it. The alcohol is a precursor to the ether, and water is a precursor to alcohol. Good. The next three reactions that we're going to look at are hydration reactions. They add water across the alkene. The first one is called acid catalyzed hydration. I don't know why I haven't been underlining this. But there are acids that you want to stay away from. For instance, over the reaction arrow, we will typically write H2O and H3O plus. But H3O plus doesn't exist on its own. You can't buy a bottle of H3O plus. You can make H3O plus in situ by dissociating a strong acid with it. But if I use a strong acid like HCl or HBr, then I risk running HX addition reaction. So we actually here, we don't want to use HCl or HBr. What we can use, what makes more sense to use, is H2SO4 as a producer of H3O plus. However, I don't always write H2SO4 over the reaction arrows. Not everywhere does write H2SO4. You can also use acetic acid. You can use toslic acid. There's a lot of acids you could use. There's no wrong answer. So because it's generic, H3O plus is often what's written. All right, here's our product for hydration. Acid catalyzed hydration. With that, I think we can add in our three pieces of information. Raise of hands. Carbocation intermediate. Yes or no? That was a weird way to phrase it, huh? Raise your hand if you think there is a carbocation intermediate in this reaction. Got one? Oh, I was expecting everyone else to raise their hands too. Natalie, do you want to explain? I added a group. Good. I added a group to a carbon that was not involved with the alkene. My structure must have rearranged. There was a hydrogen, there's not a hydrogen. That can only occur with a carbocation intermediate. Great job. Just like last time, with the carbocation intermediate, we'll see a random addition. In fact, when we look at mechanisms, we'll explain why anti-additions are locked as anti, and we'll explain why these random additions truly are random. And in terms of regiochemistry, anybody want to answer whether this is Markovnikov or anti-Markovnikov? There is a hydrogen added, yes. No, it's not anti. What happened to this carbon? It went from CH2 to CH3. So it got hydrogens. And maybe some of you are saying that this went from CH to CH2, so it also got hydrogens. That's fair. But this carbon got that second hydrogen during the carbocation rearrangement, not at the start of the reaction. This reaction should feel very reminiscent of this reaction. And all of the same notes are true. This is also a Markovnikov addition.
It really only applies like if the more substituted carbon gets more hydrogen, then it's bound to be Markovnikov reaction, Markovnikov addition. Even if the second most carbon is also getting hydrogen.
I think that we could say it in the first step. And granted, we haven't looked at the first step of these mechanisms. But I think if we can say in the first step, where does the hydrogen add, then that always justifies it. I guess it is a little strange. Is this what you're saying, that both carbons of the alkene got hydrogen?
Yeah,
How can it be anti-Markovnikov? How could it be Markovnikov at all?
that's kind of what I mean, is I
Yeah.
would've said, no, it doesn't.
I think that we can say if this hydrogen or if this carbon is a part of the carbocation rearrangement, then we stop considering it.
Oh, okay.
And so now I'm considering these two carbons. Where did the H add and where did the OH add? H added to the less substituted of the two, OH to the more substituted. Good question. All right. And as a reminder, hydration, because we added H and OH across the double bond. Our next reaction is oxymercuration. Oh man, I have been screwing that up so much. Oxymercuration reduction. There is a hyphen because those are two separate reactions. The first is an oxymercuration reaction, and then that is followed in the synthesis by a reduction reaction. Those of you that were in lab today, this is like first running a reaction and then taking it off, adding new reagents to it after the first reaction is done, and doing a second reaction. Our reagents come in two steps. First, mercury acetate and water. Mercury acetate is HgOAc2. Looks a little bit like that. Mercury takes on a 2+ charge, and it coordinates with those acetate ions. In water, this is an aqueous solution. Second, we add a reagent called sodium borohydride. We talked about the IUM suffix indicating positive charges. What does the IDE suffix indicate? Negative charges, like chloride, halide, oxide. And what we have here is hydride. That is a hydrogen anion. Hydronium, H+, hydride, H-. Can anyone remind me what reduction is? We've got mnemonics like oil rig. Reduction is gain. What better way to gain electrons, or in other words, increase the number of bonds to something less electronegative, than have hydrogen bring the electrons to share with you? Hydrogen, less electronegative than carbon. If hydrogen comes with its own electrons, carbon gets to keep them. So this second step, sodium borohydride, is a reduction step. It reduces one of the carbons. Here is the product that we get. I'm going to redraw this because I'm afraid some of you won't be able to see it. All right, truth be told, maybe I should draw it a little bit differently with that little squiggle, which is to say this doesn't add syn, it doesn't add anti. I just got mistaken. I got lost because there's only that one chiral center. Does this reaction have a carbocation intermediate like the acid catalyzed reaction does? Do you want to explain why?
It's not really rearranging.
No rearrangement. Good. The two carbons of the alkene are the two carbons that have added groups. No rearrangement means no carbocation. Instead, we have the mercuronium ion. That's where the two carbons of the alkene bond to mercury, while mercury bonds with an acetate. Okay, what does that feel reminiscent of? The halonium intermediate. So our mechanisms are sharing very common tropes. They've got carbocation intermediates, or they've got these three-membered ring intermediates that make sure the positive charge is not on carbon, that inhibit rearrangements. The stereochemistry of this reaction is random. And the regiochemistry? It's not rearranging, but where does the H add? Does it follow Markovnikov's rule, or is it against Markovnikov's rule? It's with Markovnikov. So we have two reactions right now that add water. This is a hydration reaction. It adds water across the alkene. Both of them are Markovnikov addition. Both of them have random stereo addition. But one allows for rearrangements, the other inhibits. Okay, our sixth reaction. Hydroboration. Oxidation. Another hydration reaction. We haven't done enough yet. Notice the similarities and notice the difference. Oxymercuration reduction, 2 steps. Hydroboration oxidation, 2 steps. The difference, one of them has a reductive step, the other has an oxidative step. Over the reaction arrow, once again, we need numbers. And I do want to point out that if you are asked to provide numbers and you don't have numbers, you lose points for that. Because without numbers, you're saying, I'll go down into the lab and I'll mix all of these reagents at once and nothing will happen. Or worse yet, something bad will happen. But by having the numbers, you're saying, first, I will add this and I will let it react. Then, once the reaction is finished, I will add that. That's an important step in organic synthesis. Here, 2 steps. First, BH3. BH3 is a chemical called borane. The usefulness of borane is the electronegativity of boron. Boron is less electronegative than hydrogen. Who owns the electrons from the BH bond? Hydrogen. The second step is basic aqueous hydrogen peroxide. H2O2, H2O, and NaOH. Basic aqueous hydrogen peroxide. I'd like you to turn with your groups and discuss. Is there a carbocation intermediate? How would you describe the stereochemistry? How would you describe the regiochemistry? I'm going to make some space on the board. Well, that's not a hydrogen. That's an O.
I'm not sure about that. The one that was right here has just here we have this.
Here we have this. But in these other positions, we have O. So the H acid is anti-carboxylic. Good. Yeah. Or maybe during the break a little bit. Or I'll go down. Yeah. Right.
You can answer this question.
Is there a difference? Okay. Look at how all of them connect, right? We're looking at the intermediate, we're looking at the regiochemistry and stereochemistry. What do you think, sir? That's fine. Yeah.
Yeah, we're just caring. Oh my gosh. Just caring about if we're adding.
Yeah. Which we call that goes directly against.
Yeah.
So it's not okay. It's not against. It's not. Someone probably talks to them. Exactly. Like the hallucination reaction. That's a good point. You wouldn't use that.
Yeah.
I've never heard of
We're
it.
talking about acids
So I want to talk a little bit about the intermediate and how it forms. If we look at our alkene and we recognize that there was a partial positive and partial negative region, can anybody remind me how we got to those partial charges? Because carbons don't have a difference in electronegativity. That's generally how we produce partial charge across bonds. So what did we use to validate that these partial charges make sense? But I don't see any lone pairs here. But what did we use to show a lone pair from this? We looked at its resonance form. And we said in the resonance form, there's one resonance form that puts the lone pair in a region where it doesn't have a lot of repulsion, and we put the lone pair in a region that has a lot of repulsion. And it would prefer to be in a region with less repulsion. That's what you were getting at with the lone pair, right? So we used resonance to say that this is a more valid, that these are valid partial charges. If the electrons of the pi bond were to be taken and lost by one of the two carbons, this is how they would be preferred to be taken and lost. Stability of charge. Now let's take borane and let's line it up against this, aligning partial charges in the way they prefer. H with a partial negative, boron with a partial positive. We align the partial positive to the partial negative of the carbon. We align the partial negative of borane to the partial positive of the carbon. And that's the regiochemistry that we get. The hydrogen adds to the carbon that is more positive. If we were to show arrows here, we would say hydrogen takes its electrons, gives them to the partial positive carbon. Carbon takes its electrons, gives it to the partial positive boron. So we don't have a boronium intermediate. This isn't like the halonium intermediate. It's not the mercuronium intermediate, but it's also not a carbocation. We just get a borane structure. Boron connected to the carbon. And the regiochemistry is all validated by the partial charge lineup. Oh, sorry, that was not really what I wanted to put. Compare that to one of our HX addition reactions. Where the partial negative of the carbon is attracted to the partial positive of the hydrogen. Now we've got this flip. It's the partial charge of hydrogen that is impacting the regiochemistry of these reactions. When hydrogen is partial positive, it's the less substituted carbon that takes it. When hydrogen is partial negative, it takes itself to the more negative carbon. The more positive carbon. Partial charge on hydrogen predicts the regiochemistry. Okay, and in my opinion, if a rule has to be named opposite of you, it shouldn't be named after you at all. So here's the intermediate. It's important to say there's no carbocation intermediate. This reaction is syn addition, and the regiochemistry is described as anti-Markovnikov. Elliot had a great point. He thought maybe we could call it non-Markovnikov. But the fact is it goes directly against Markovnikov's rule. The hydrogen added to the carbon with less hydrogen. It is anti-Markovnikov's rule. It's exactly opposite, which tells you Markovnikov's rule is meaningless.
What did this guy do to you?
I don't know. I think I need a scapegoat. You know, you can't make me the bad guy. I didn't invent this shit.
No, I already did.
And they're dead.
Yeah.
Exactly.
Yeah.
So I would argue that all of the regiochemistry in this chapter, it's all governed by charge stabilization. Partial negative to partial positive. Yeah, that makes sense. Partial negative to partial positive. Yeah, that makes sense. We're going to come back to look at this reaction, and we're going to say the same thing, that there will be a partial negative on the solvent that goes to a partial positive on the more substituted carbon. That always explains your regiochemistry is charge stabilization. But for right now, let's take a break. We've got two more reactions that are not alkene addition. I'm sorry, not hydration. Woohoo! And then another three. So let's take a break. 5 minutes, get your blood flowing, and we'll come in and wrap these up. And with the spare time, we're going to practice on the back. But actually, you're more than welcome right now to start predicting products on the backhand side. I have given you a clue about how many products will form. On the sides here in parentheses, I'm showing you the total number of stereo or structural isomers that can be generated. So you don't have to guess at how many to draw. There should be that many. Deal? All right, let's take 5. Let's be back at 6:10. Is there a different position that we might use this in? Sunglasses? All right. Yeah, exactly. That sucks. I spilled some hot oil on me, I think yesterday for lunch. Moving the pan around. Can't imagine. You'll never make popcorn without safety glasses again. Man.
I'm sorry, I had to go. I'm so fucking mad.
Yeah. This is a good question. Let me see if I can. Let me see if I can rephrase it. In this mechanism, there are two arrows in one step. Both groups add at the same time. In this mechanism, there are two arrows in one step, but both groups do not add at the same time. That's right. So this gave us a carbocation intermediate where the hydrogen added, but the halide was produced as an ion. That is what allows for the carbocation rearrangement to occur before the halogen comes in as a nucleophile and bonds. And we're going to look at the mechanisms more, so this is really just like quick and dirty, yeah? But I actually thought about orienting this the other way so that you could see the partial negative line up with the partial positive. But I also didn't want anyone to accidentally draw the exact same arrows because these do not have the same step. If they did have the same arrows, there'd be no carbocation, there'd be no rearrangement, and yet we know that to be true of this product. Yep, good question. All right, two last reactions. We have added one hydrogen, one halogen, two halogens, one halogen, one oxygen group, actually two different oxygen groups. One hydrogen and an oxygen group in three different ways. It's time we add just two hydrogens. No, I'm just kidding. Two oxygen groups. This reaction is the diol addition. There are actually two different reagents that we can use. The one that I like is osmium tetroxide, OSO4. I've been told that my handwriting font makes that look like O5O4, but that is the transition metal osmium, OS. Or you can use the reagent potassium permanganate so long as you run it cold. Ooh, some of you did this today. You took an alkene, you mixed in potassium permanganate at room temperature, and what did you make? Well, you didn't analyze it, to be fair, but the procedures did tell you. It made brown.
Or purple.
Okay, well, the chemical that it made that left behind a brown precipitate was a vicinal diol. This reaction is syn addition. I do want to point out the last two syn addition reactions, I only showed one of the stereoisomers, but I want to be clear that if they can both add wedged, they can both add dashed. That means that you can get a mixture of those chiral centers, if any. The regiochemistry, I'm not describing as Markovnikov, I'm not describing as anti-Markovnikov, and I'm not describing as solvent adds in a specific spot. Instead, I'm describing it as a vicinal diol. Vicinal here means adjacent or in the vicinity of. And that's different than just having two alcohols on a compound. A diol could have been 1,4-butane-diol. But this is a vicinal diol. Those two alcohols are on adjacent carbons. There's also a geminal diol. Anybody a Gemini star sign? What does that mean, Natalie? You know? The Gemini? Twins. And the geminal diol are when the two alcohols are attached to the same carbon. They're twins. So, specifically, vicinal diol in this case. Good? The last reaction, 8, is the I'm sorry. It starts the same, it ends different. Hydrogenation. Or in other words, H2 addition. This is a reaction that those of you in lab will do next week. You're going to hydrogenate a fatty acid and you're going to make it a saturated fat. Try to take a liquid fat and turn it into a solid. It doesn't always make a solid, and that's usually because it's not a pure mixture. In order to do hydrogenation, we need hydrogen gas, H2, and we need a catalyst. The catalyst that we often use is a transition metal catalyst, palladium, and it needs some molecular scaffolding, so we use charcoal, which is carbon. So we write the catalyst as PDC, or palladium on carbon. That's how it's pronounced. A few things I want to say here. H2 is always in excess. It is very challenging to get a gaseous reactant and limit the amount that you're adding in. To use H2 as a limiting reagent is nearly impossible. So anytime you see something like H2, you should always assume it's in an extreme excess. Also, instead of palladium, we can also use platinum and nickel. These are all in the same family, so they all have very similar catalytic functions. Okay, now the result is an alkane. Hydrogenation takes alkenes and reduces them to alkanes. But if you want to highlight the stereochemistry, this reaction is syn addition. In my opinion, there's really no point in even discussing if there's a carbocation intermediate. You'd never know because you're adding hydrogens all the way around. And there's no point in describing the regiochemistry because you're just adding hydrogens. So everything else is pretty much the same. However, it is important to say there is no carbocation intermediate. And if you wanted to describe the regiochemistry, this is maybe where you could say the regiochemistry is non-Markovnikov because it doesn't really follow his rules. Certainly not anti. I would probably just put Na. Regiochemistry doesn't really apply here. Do you guys have any questions on these first 8 reactions? Non, because Markovnikov's rule is hydrogen adds to the carbon with more hydrogen. Well, hydrogen adds to both carbons here. Yeah. So it doesn't really follow Markovnikov's. In the same way that halogenation is non-Markovnikov, doesn't follow Markovnikov. And the halo ether is non-Markovnikov because there's no hydrogen involved, so you can't really apply it there. Okay, we've got 3 reactions left. One of them will feel very much like the others. The other 2 will not feel like any of the other alkene addition reactions. And spoiler, we're actually going to come back in Unit 5 to add on an addition reaction to the alkenes. Okay, first, going up, we're going to look at epoxidation. The reagent that you will see most often for epoxidation is MCPBA. And I'm going to tell you what MCPBA is, and I'm going to tell you the more generic version of that chemical. MCPBA stands for metachloroperoxybenzoic acid. Anytime you hear peroxy or even per, we're generally talking about a higher oxidation state or additional additional oxygens. A peroxy acid is a functional group that doesn't just have carbonyl to OH, but has carbonyl to OOH. It has a peroxide bond, an OO single bond. We can abbreviate peroxy acid as RCO3H, and if you put RCO3H in place of MCPBA, you get full credit because MCPBA is an answer to RCO3H. Epoxidation feels a little bit less like all of the other addition reactions because I don't add 2 groups. I only add 1 group to both carbons. In fact, we say that addition reactions consume a degree of unsaturation, although typically we're looking for the consumption of a pi bond. And in this case, I do not consume a degree of unsaturation. I just translate a pi bond to a ring. I keep the same number of degrees of unsaturation. There is no intermediate. I don't know that it's useful to say there's no carbocations. You can see the 2 carbons of the alkene become the 2 carbons of the epoxide. The stereochemistry is clearly syn addition, but there's really no alternative. Between 2 carbons, connecting them to a shared group has to be either above those 2 carbons or below those 2 carbons. It can't be both above and below those 2 carbons because that would actually just be within the 2 carbons, and that's no longer shared by them though. And again, the regiochemistry, kind of Na. There is just those 2 carbons that turn into the epoxide. Our last 2 reactions are both considered oxidative cleavage. And these are the 2 that will feel the least familiar to all of the other alkene addition reactions. They look nothing like alkene addition. The first one is reductive ozonolysis. Ozonolysis is a form of oxidative cleavage. This is a type of ozonolysis that is more reductive than most. So this is an oxidation reaction. It's just not the most oxidative it could be, so it's referred to as reductive ozonolysis. The reagent that we need for reductive ozonolysis is O3 with DMS or with zinc. O3, of course, is ozone. DMS is dimethyl sulfide. I think somebody shared dimethyl sulfide for us when we did functional groups. Does that sound familiar? Or was it dihydrogen sulfide? I think you guys had dimethyl sulfide. The product that we get in this ozonolysis, in this one it's actually two. Notice how I've taken the carbon chain of the starting material. I'm going to number this here from left to right, 1, 2, 3, 4. Notice how the carbon chain has cleaved the carbon-carbon double bond, and it's now produced two carbonyl products. Cleavage of the double bond, oxidation of the two carbons, oxidative cleavage. You'll notice that 2 of the 3 oxygens have been consumed by the carbonyls. Where is the third oxygen? It's transferred into the reducing agent DMSO, it's transferred into the reducing agent DMS, which becomes DMSO, dimethyl sulfoxide. There is no like stereochemistry to consider here. An sp2 carbon becomes an sp2 carbon. But there is a little bit of regiochemistry to consider, and that would be ketones and aldehydes are possible. Depending on the substitution of the two carbons. That's why I've chosen this alkene starting material to highlight the two possibilities that you can make. One of the carbons is attached to 2 other carbon groups, it becomes a ketone in the product. The other carbon is attached to only 1 carbon in the product, in the other carbon groups, it becomes an aldehyde. Those are your possibilities from reductive ozonolysis. Ketone, aldehyde. Technically, there's a third option, which is formaldehyde. And formaldehyde is no carbon groups attached. If I had just a CH2 carbon, I would have formaldehyde. The other reaction is called oxidative ozonolysis.
Wait, just real quickly, so is there no intermediates?
Certainly not one that you want to be tested on.
Okay.
There is an intermediate, several. They're very complex. I can't intuitively predict the mechanism. In fact, there's parts of the mechanism where the 2 fragments break away from each other and then reconnect in a different sequence. And to me, that seems very strange.
So no meaningful intermediates?
True.
Yeah, okay.
No meaningful intermediates. I'll show you guys what the intermediates look like because it's interesting, but it's not productive. Oxidative ozonolysis, the only difference is the additional reagent we give? O3 with hydrogen peroxide. But there is another way to do oxidative cleavage that is also very similar to the oxidative ozonolysis, and that is if we use hot potassium permanganate. What did we get with cold potassium permanganate? Vicinal diol. Hot potassium permanganate will cleave that double bond. Here are the products: ketone and carboxylic acid. So in terms of regiochemistry, there are two functional groups possible. Ketones are possible, carboxylic acids are possible. I've given you a specific molecule where oxidative cleavage forms one ketone and one carboxylic acid, but I think you can agree that there are molecules that form two carboxylic acids. It all depends on what the combination of your combination of your carbon substitutions are. Can you see now why blue is considered reductive and orange is considered oxidative? What is the difference between the two products of reductive ozonolysis and oxidative ozonolysis? Not an alcohol. The OH group. Notice how the hydrogen connected to carbon 3 remains unchanged in reductive ozonolysis, but gets oxidized to a carboxylic acid in oxidative ozonolysis. More reduced carbon, more oxidized carbon. Oxidative cleavage, reductive oxidative cleavage. Both are oxidizing the carbons. One is doing it less so. All right. Those are our, what did I say? 11 reactions for this chapter. And next section, we're going to learn more reactions with alkynes. The section after that, we're going to learn a few more reactions with alkenes and dienes, and then alcohols and alkyl halides as well. I want to give you guys an idea of how to organize all of these reactions. This is one tip. It's a reaction diagram. It takes a common starting material and shows you all of the various functional groups that you can make from that alkene and all of their different reagents. Another thing that I did only once I started OChem 2 that I wish I had started doing in OChem 1 was a table of reactions. The best way to do this table, and this table takes a lot of time, takes a lot of effort, takes a lot of reworking. That is the process of getting these reactions down. So don't be upset when you spend hours building this table of reactions, reworking things, trying to figure out what are good examples, because that is hours spent studying. The way that I recommend setting up a table like this is to look at what functional group you have in the starting material. For right now, that's just alkenes. Functional group of your starting material, the reagents that you can add to it, the notes that you have about that reaction. Is it syn addition? Is it anti-addition? Does it have a carbocation rearrangement potential? Does it have a halonium ring? And then lastly, the functional group of the product. Does it form an alkane from the alkene? Does it make a diol from the alkene? Does it make an alcohol from the alkene? Does it make a dihalide? Does it make a vicinal halide ether or a vicinal halide alcohol? Building a table like this, it allows you to organize all of your notes, summarize all of it, and then when you start doing your homework and you're studying for the exams and the unit tests, you're able to glance back at this quickly and pull out the information you need more quickly. Sometimes the reaction diagram is also helpful for that, but I know for some people the reaction diagram is a little bit cluttered, a little bit challenging to look at. So this is a big task. It's not one that's graded, but students that do well on their final oftentimes have spent time trying to make something like this. So I recommend it. You can also make money from it if your classmates want to pay you. Any questions on our last few reactions before I erase them? One more resource that I want to show you guys. As we get into this series of organic reactions, I want you guys to get some tangible idea of how these reactions look. So this link on our homepage, ChemTube 3D, it has a lot of the reactions that we're going to look through this semester. You can go to the organic drop down, and then it gives you all of the different categories that it has. We're doing predominantly electrophilic addition to alkenes. Let's look at this peroxy acid mechanism. Notice the alkene is flat. You guys see how that has a top face and a bottom face? Here's the top, here's the bottom. Right now, it looks like it's reacting from the top face. That means whatever group we add, we would show it with wedges. What is the likelihood that this reaction could also happen from the bottom face? 50-50. So when you create chiral centers and you're not sure whether the group should add wedged or dashed, it's both. Alkenes are able to add things to their bottom face to become dashed groups. They're able to add things from their top face to make wedged groups. For some of these, it also has the mechanism. So let's watch the epoxidation mechanism. Wow. And then it will reverse it for you. Notice the peroxy acid is donating one of its 3 oxygens. And the carbonyl oxygen becomes the carboxylate oxygen, the OH, the carboxyl oxygen. And then you can see how this is added to one face. So that's a wedged epoxide, and the way it's oriented, it looks like it's wedged, but now I've oriented it so that it looks like it's dashed. There's another reaction I want to show you, which is this one. This is a halogenation reaction. What alkene am I working with here? Butene. Need a little bit more information. 2-butene. cis-2-butene. Good. That's specific. That's a different stereoisomer than trans-2-butene and a different structural isomer than 1-butene. And all three of those give very different halogenation products. So, again, I could form a halonium ring from the top face or from the bottom face, really just depending on how I decide to orient myself. Here's that halonium ring. 2 carbons of the alkene and the bromine. The bromine takes on a positive charge, and this bromide takes on a negative charge. Now, from that halonium intermediate, the halide is only allowed to attack from opposite the halonium ring. So we talked about this reaction being anti-addition. One group will always add on one face, wedged. One group will always add on the opposite face, dashed. That's because the first bromine to add takes up the entirety of that face. It takes up both wedged positions, or, depending on how you want to look at it, both dashed positions. And I want to ask you this. Did you notice how from this step, the halide ended up all the way up here at the top? And then to the next step, I need the halide to be all the way down here on the bottom. That's not exactly easy to do. That halide needs to move through physical space, surrounded by solvent molecules, to find itself in the right place on the molecule to react. And then it can react. It forms a bond with one of the carbons and breaks that bond in the halonium ring, wedged, dashed, anti. We call this a backside attack. This halide is attacking opposite of where the group is leaving. It's attacking from the backside of the bond. All right, well, that was stereo-specific, but what about regio-specific or regio-selective? Here's another halonium ring formation. This is 2-methylpropene, but we can see that it forms the halonium ring. Whoa, do you see that? That halonium ring was not an isosceles triangle, was it? It's severely slanted on one side. Why? Well, the carbon that can hold a positive charge better is relinquishing the electrons quicker. This more substituted carbon, it deals with the electrons less. It allows carbon to hold on to them instead. That means that there's a strong partial positive on this carbon. And what attracts a partial positive? What does a partial positive attract? It attracts a partial negative. So here's the partial negative of the oxygen and methanol, and it's attracted to the partial positive of the more substituted carbon on the halonium ring. Partial negative of the alcohol attacks at the more substituted. Do you guys remember what your notes were for the halohydrin, haloether addition? We said the solvent attacks at the more substituted position. Why? It's where the charge is stabilized best. It's all about charge stabilization. This is both stereo-specific and regio-specific. It will always go to the more substituted position. Wedge group, dashed group. You guys start to see it a little bit more clearly with these 3D models? Because now we're going to do mechanisms. We're going to show this arrow pushing. We're not going to show these transition states quite as much. And the mechanisms can feel, again, a little intangible, a little abstract. We're demonstrating this. We're demonstrating the donation of electrons, the taking of electrons. We're demonstrating bonds forming and bonds breaking. And we're going to use stereochemistry in the mechanisms. We're going to remind ourselves that the halonium ring is syn addition, and then the nucleophile attacks and adds anti. So come to this resource while you're working on your homework if it helps you remember what's happening in 3D space. Try to get a feel for it. Play around with more examples. All right? We've used up most of our class time. Oh, shoot. No, I shouldn't have done that. So I think with our last few minutes, here's what I want us to do. I'm going to break you into groups to solve some of these problems that are on the back of our worksheet. And we'll see what we get. So, front table right here. I would like you to give me this ozonolysis product. And I'll give you a hint. In class, we saw that when you cut this, you get two groups. But in your problem, those two groups are connected to each other. Deal? Next table. You guys will give me the two products that form from the hydrogenation just above that. This table up here, I'd like you guys to solve these two, the chlorination and the epoxidation. This has 4 products. So the table in the back, I want you guys to think about how you can get these 4 products here. Okay? And then this table in the middle, and Elliot, you guys can work on these hydration problems. All right, see what you can solve in the time remaining. And I'm going to come around and answer questions that you have. So here's a tip for you guys. You've identified it as reductive ozonolysis. Okay. So you're going to you can redraw the structure and elongate that carbon-carbon double bond, and then just erase them and put carbonyls there instead. That's the shortcut way to always solve for an ozonolysis product. Just redraw the structure, break the double bond, and put carbonyls instead. What are your first 4 carbon chains? ET2O is diethyl ether. So ET stands for ethyl. Yeah, so this is ethanol. ETOE. So we're actually running a little hydrogen or halo ether. reacting with water.
Yeah.
I am reacting with alcohol. Alcohol is a precursor to alcohol.
Less substituted carbon.
This is the halo keeper. Correct. The alcohol was produced in ether products. But you get a 2 pages.
Oh, the back.
No, it's
Or you can restart if you want. Like if you didn't like your midterm sheet, you can start it. Yeah,
Okay.
exactly. And it'll be not, there's
It's
always
always
a
described
straight
as looking at
like halogenation, straightforward. But maybe halo ether is confusing enough. Yeah. Good work, guys. Nailed it.
No, that was one.
Good job. Oh, I didn't know there was The only thing that I would show is that a squiggle or is it a dash? Okay. Because the squiggle means I'm not sure which one it is. We actually know that it's wedge and it's dash. Those, the wedge and the dash, are the 2 product types. Yep. Good job. Great work. You guys all agreed? Good. And now, like you guys have shown the wedge and the dash, even on the achiral carbons, you don't have to. Because it's achiral, so that primary carbon to the chlorine, doesn't matter if it's wedge or dash, it can rotate in all positions. It's achiral. Sure, or just a straight line. Because its absolute configuration doesn't matter. You only created one chiral center. This one matters at this position. But it doesn't matter here. So you've done it in a way that highlights that you know it's anti-addition, but actually the chirality or the stereochemistry on the achiral position is all of them. It can rotate through all of them, so it doesn't matter. So what I'm trying to say is when you make a chiral carbon, you should show that you form both versions. When you form an achiral carbon, it doesn't really matter. All right, guys, I have taken you past time. So whatever progress you've made so far, good work. We'll pick up with these problems at the start of Wednesday's class. And then we're going to study 4 mechanisms on Wednesday. We've learned 11 reactions. I'm asking you to only be able to show me 4 mechanisms. You're welcome. Those 4 are the most important, in my opinion, to understanding any other reaction. If you can master those 4, you'll have the skills to interpret or predict or understand other mechanisms that you see. That's our goal on Wednesday, 4 mechanisms to wrap you up for the unit test. All right? Have a good night.
You only have to,